In this lecture, what I'm trying to do is just to give you a flavor. I mean, if I want to go deep into this, this will take quite some time and very exhaustive and extensive work. Uh, in this one, I'm just giving an example of a singular function. Okay, so this is known as the Cantor function, or the devil staircase function. It's very funny because one may wonder why not the angel's staircase function, but in any case, if you Google it, you will find that mathematicians are calling the devil staircase function. Okay, so what is, first of all, before I move a little bit more, is what is a singular function? Okay, that is so definition. So you have a function f defined on AB into R. So we say that f is singular if, and only if, number one, f is continuous. Okay, so this is very important for later on for the Riemann integration and Borelian functions. Two, okay, f is almost everywhere differentiable which means but before hold on, let's just continue. And f prime of x, the derivative, is 0. Okay, so wherever it is differentiable, the derivative is equal to 0. What does that mean, almost everywhere? Let me give the correct definition. It means that there exists a set n which is with measure 0 such that f is differentiable on AB minus n. So of course, if you are wondering why n is for negligible, so sometimes we call it negligible as well. So a set of measure 0 or a set which is negligible is okay. And of course, the third condition, and this is very important, is that f is not constant. Okay, so this is very, very interesting because assume that you have a singular function, then automatically the formula here, the fundamental theorem of calculus that tells you that this is f of b minus f of a fails, for the simple reason that the derivative is going to be equal to 0, and then of course you have the integral over any sorry, let's call this prime a prime b prime a prime. So you're going to have any two numbers, the derivative is equal to 0, okay, we said, and then of course the integral of the 0 will give us that f prime of b, I mean f of b prime is equal to f of a prime, which means that f is constant. But f is not constant, and therefore this relation will not work. This relation, or this conclusion. In other words, that f prime is bad. So this is the idea here. Okay. So this identity is valid if f prime is nice. So in this case, if you have a singular function, f prime is not nice to allow for this identity to hold. Okay, so this is the beauty of this function. So first, can we find such an example of this type of functions? And they have some amazing this properties 1, 2, 3 of singular functions. They imply some amazing properties on the existence of some sets such that this implies this, etc., etc. I don't want to go into details. The point is, do they exist? Such examples of functions, do they exist? And so this is what we are going to discuss next. Give an example of a singular function. So the example is, so let's go back in order to, so this is the Cantor function. And why Cantor function? Because it's built on the Cantor set. So we're using the construction of the Cantor set. And what I'm going to say right now, it's really interesting if you go back to the lecture on the Cantor set, how we can have a more diversified constructions of other Cantor sets, and therefore from there you can also see how you can build some Cantor functions at the image of what I'm going to be doing right now. Okay, so let's start with the beginning. Okay, so we have 0, 1, and we have so we remove the first interval. Okay, so now what do you do? What we do, we take the interval 1/3, 2/3, and we take the function that gives you 1/2, okay, on that interval, and you make it continuous by going from 0 you get 0, and for 1 you get 1. So you go like this and like this, and let's call this function f1. Okay, so this is the first function for us. Second function, so we go again to 0, 1. So we have this interval is out, and then we have these intervals. So this is all out. Okay, so in order for us to understand this one, we go by divide by 3. So it's 1/9. So there you have 0, 1/9, 2/9, 3/9, which is 1/3, 4/9, 2/3, 5/9. Oh, hold on. It's always the problem I have with this 4/9 and 5/9. Okay, so 2/3, that's 6/9. 5/9 and 4/9 are in between 3/9 and 6/9, and this is 7/9, 8/9, and then 1, which is 9/9. Okay, so now what do? You go here and you put 1/4, and then this one will be 2/4, and then this one will be 3/4. Okay, and then 1. So we go like this, like this, like this, and like this, and that is your f2. Okay, so let us, so this is 1/3, 2/3, and this is 1, so you can see it better. Okay, so all these functions, they go from 0 to 1. Okay, and then on these intervals you start, so the next one will be what? For the next f3 is going to be 1/8, etc., etc., and you keep going up, 1/8, 2/8, etc., etc. So keep in mind that, just to give you an idea, on this interval here, which is the same as this one, f1 and f2 coincide, and even if you go to f3 they will be equal, right? But if you go from f2 to f3, they coincide here, etc., etc. So the sequence here, when we go to the next one, so what happened at n? 0 to 1. So first of all, how many intervals did we remove? So there are all these little intervals, etc., etc. They are out. So there are 2 to the power n minus 1 intervals out. Okay? So on these ones, the first one you go 1 over 2 to the power n. Okay? That's the value, the constant. Huh? And then on this one, you go 2 over 2 to the power n. And the last one will be 2 to the power n minus 1, minus 1 over minus 1 over 2 to the power n. Okay? And it's very interesting to see this is your fn. If you go from fn to fn plus 1, they coincide on these intervals, because the intervals, the one that you removed, they are still removed in the next level, and you remove more. Okay? So what's interesting is, if you want to see a picture of the graph of these fn's and what happens when n become large, here we are. So this is f1, f2, f3, etc., etc. So what are the properties of this fn? So of course here, I'm sorry, so you keep going till you get to f when n goes to infinity. So we let n go to infinity, okay? And these fn's will converge uniformly, in fact, to f. So what are the properties of f, okay? Number one, as I said before, if you look at fn, starting with fn, and you go fn plus 1, fn plus 2, they are all equal on these intervals, okay? And therefore, f coincide with all of them on these intervals that we are removing, okay? Great. So what's left at the end when we go to infinity? So on these intervals, we know what f is, okay? So what's left? What's left is exactly the Cantor set. So f, of course, is known outside of the Cantor set. So here, f is well known on 0, 1 minus the Cantor set, okay? Because this is where we have the fn's, okay? Great. So what's interesting also is that on these intervals, on each interval in 0, 1 outside of the Cantor set, f is constant, okay? And therefore, it is differentiable, and its derivative is 0 on these intervals, okay? Because the function f is constant, okay? Great. What else? We know that the intervals that you removed, their measure is 1, and we know that the measure of c is equal to 0. So basically, f is differentiable outside of a set of measure 0, and its derivative is 0. Great. 2. F being a limit, a uniform limit of continuous functions, f is continuous on 0, 1. Okay? So we have a continuous function on 0, 1. It is differentiable outside of the Cantor set. Its derivative is equal to 0. And we know that the measure of c is equal to 0. Now, is the function f constant? No, because if you look at fn of 0 for every n, and therefore f of 0 is equal to 0, while by construction fn of 1 is 1 for every n, so f of 1 is equal to 0. I'm sorry, f of 1 is equal to 1. So you see the function is not constant, okay? Continuous, it goes from 0 all the way to 1. In fact, it's also, by looking at the graph of these functions fn, they are all the fn's are monotone increasing, not strictly increasing, monotone increasing, okay? Which implies that f is monotone increasing. increasing. So it's not just a singular function, it's also a singular function, which is what? Monotone increasing. So we have now a function f, which is built on the Cantor set, on the complement of the Cantor set, using the construction of the Cantor set, which is singular. So it's very, very, very beautiful. Now, fine. So we have this limit. There are other constructions that one can find in the literature, which it gives you properties, some weird functions, but here let's go back to this one. What I'm interested in is there a formula for f of x? This is very interesting. Is there a formula for f of x? Okay, and that's interesting. So let us try to understand what's going on. So first of all, when you take x in 0, 1, so this is a beautiful question. So we take x in 0, 1. Okay? So if we take, because we are dealing with the Cantor set, so we have to consider the ternary expansion, or the expansion the expansion in base 3. So x will be equal to 0, comma a1, a2, a3, etc. And we know that all the an's are equal to 0, 1, or 2. This is the expansion in the base 3. Okay? So if you look at x in C now, okay, C is exactly the ones for which an are either 0 or 2. Okay? So we have seen this. If you go to the lecture I did on the Cantor set, you will see that exactly the element in the Cantor set are the ones with 0 or 2. Okay? So if you have a point, if you have 1, okay, and with something after it, then you will be in the complement. Okay? So in any case, so how do we define now f of x? Okay? So this is how you do it. So it's interesting here. So f of x, what you do, you look at the first, okay, so you have x, you go and you look at the an, in the ternary expansion of x, and say you have the first one that's equal to 1. Assume that you have 1. If you don't have 1, it means that you are in C. Okay, if you don't see 1. But if you see 1, the first one that you see there, what you do, you truncate x. Okay, you go and you do t of x, okay, which is just 0, comma a1, a2, an0. Okay, so you truncate it and you put all zeros after that. So we know that, of course, this one, so we have an0 minus 1, 1, so that's the first. So the ones before here, they are all 0 or 2, because we said the first one we are going to meet is 1. Okay? And now what do? You go, and you go and you come up with the number y, which is same 0, and you take a1 over 2, a2 over 2, an 0 minus 1 over 2, 1. But this time in base 2. Okay, so keep in mind, we said that all these numbers are AIs are all either 0 or 2, so I can divide them by 2, basically, right? Okay, so basically here, what do we have? Just to give you an analytical formula, tx is sigma of AI over 3 to the power I from 1 to n0 minus 1 plus 1 over 3 to the power n0. And to this one, you associate y, which is sigma 1/2 AI 2 to the power I from 1 to n0 minus 1 plus 1 over 2 to the power n0. Now, what happened if there is none? Okay, this is easier. So if x belongs to C, okay, we know that you don't have, so it's equal to 0, comma, a1, a2, etc. And they are all, so you divide by 2 and you are done with it. So this, in this case, you go straight to y, which is 0, a1 over 2, a2 over 2, etc. in base 2. Okay, meaning what? That you have sigma of ai to the power I from 1 to infinity, and you're looking at, this is x, and you're looking at y equal 1 half. You divide each one of them by 2 to the power I from 1 to infinity. So what's interesting is that in this construction, in fact, the y is f of x, and this is interesting. So we do have a way of seeing of x. Keep in mind that what we are using is this expansions in different bases. This is what mathematicians were playing with in the late 1800s, beginning of 1900. That was their bread and butter of creating some weird and complicated what functions. The references here, if you go back, you will find, I don't want to dwell too much on this, but you can go and find all these big mathematicians during the late 1800s, beginning of 1900, who were playing with these functions here with some very awkward and weird behavior. Okay, so let me just show you very simple. Like for example, if you look at 0, 1, and you look at 1/3 and 2/3. So in base 3, what does that mean to be in the interval 1/3, 2/3? To be in the interval 1/3, 2/3, this means that you start with 0, 1, and something. Okay? So what did we say? We said that we are going to truncate everything. So this is your t of x. So this is x. Okay? So it becomes 0.1. Okay? And then from there, we go to the base. So it's going to be 0.1 on base 2. Okay? And in base 2, this is exactly 1/2. So any point in here gives you, the image will be what? 1/2, and that's what's good. But I will leave it to you to look at, for example, what happened to the case where you have the other two, and you will find it's exactly the same, that the function f is constant, and it gives you the value of the function that you have there. This function, by the way, it's continuous, the one that I just described using this construction, using the expansion, okay, either the ternary expansion to the binary expansion, you can easily show that this function, in fact, is continuous based on this, okay? Because if x is very close to y, they have the same coefficients there, up to a certain n, of course, okay? And becoming larger and larger as x gets closer and closer to another point. Okay, quickly before I close this, I want just to mention that recently there's something very interesting, which is that a Japanese physicist, okay, his name is Hiroki what was his name? Hiroki Wadati. So recently, while they were studying some magnetic material, to be precise, the cobalt oxide, SRC06011, that when they were studying this, they saw, while studying the magnetic properties of this cobalt oxide, they saw this kind of devil staircase behavior, or the Cantor function behavior. So it's really amazing. In fact, it even allowed some to get three physicists to get the Nobel Prize using some other phenomena. But anyway, so the point is, these kind of functions are having some major impact in theoretical physics. Okay, thank you.